Hey everybody, how's it going? I've been talking a lot about strings lately, and one of the things that comes up a lot when talking about strings is security. When I posted my first beginner strings video, I very predictably got this comment, and you're gonna hear all over the place people say, don't use string copy, don't use it, don't use string copy, it's unsafe, it's going to get you hacked. And I didn't mention any of this in my previous video because my focus was on simplicity. I wanted you to really understand the core of how strings work in C and not really initially worry too much about getting hacked or about security. And security tends to add some complicated details that I didn't want to get into. But I think it's time, so today we're going to talk about programming decisions that you can make that could get you hacked. Now, there are a lot of things we could talk about security. There are a lot of ways that an attacker could compromise software that you write. Today, I just want to talk about one of them, and that one relates to strings. Specifically, I want to talk about buffer overflows. Sometimes they're called buffer overruns. The idea is simple. In C, a string doesn't have a built-in stored length. In Java they do, in Ruby they do, in Python they do. All of these languages store a length with your string that tells you how much space is available for that string. But in C we don't do it that way. We just know we're going to start at a location in memory and we just march along until we hit a null character. That's 0 that tells us that we've reached the end of the string. And that's how functions like string copy work. They just march to the end of the string and they just keep going until they hit a null character. So what does that have to do with security? Well, let's look at an example. Let's say that I use string copy to copy a string into an array that I declared. Let's say I give it 10 bytes. Now the problem is that string copy doesn't give me any way to guarantee that the source string, the thing that's copied in, is going to fit. String copy doesn't know how big the array is, so it's just going to copy characters until it reaches a 0. And if the string that we're copying in is too big, then we're going to overflow our array, or our buffer, and that's why it's called a buffer overflow or buffer overrun, and that can cause us some problems. Okay, so let's look at it. For today, I want to use a very simple demonstration. We're going to write a very simple program. It's going to take 2 arguments, a password and a string that I want to print out. Now with a real application, it would probably be something more sensitive, but this will be good enough for demonstration purposes. Then let's make 2 arrays, 10 bytes each for simplicity, and having passwords in plain text is another really bad idea, but let's ignore that for now. We can talk about secure passwords in a later video. For now, we're talking about buffer overflows, so this will do. Now, we're going to copy the message into the buffer array. Now, this is kind of arbitrary, but let's say that I copy the message into the buffer array, and then I check the password using another little useful string function, or string compare, and if it matches, we print out the buffer. And if not, we'll print out an error. Now, this is a really simple example, and there are different ways you could do this, but I think that this will do for today's purposes. I'm also going to test this on Linux today. This specific example may not work for you depending on the compiler or compiler version you're using, but hopefully you can adapt it to your own setup once you understand the principles involved. So let's compile our stupid little test program, and notice that if I run it with the correct password, it works as expected. And if I run it with a bad password, it prints out an error just like we want it to. Now let's put on our security hats and play bad guys for a minute. And let's see if we can break this program. And I mentioned that hard-coded password is a problem. Just to quickly show you why, we can use the strings utility, and it's going to dump all of the printable strings in a.out. And I don't necessarily know which one is the password, but I can try all of them. There aren't that many, and eventually I get it right. I could also disassemble the binary and look at the assembly code, and that might make things even easier to figure out. But that's not the attack I'm really interested in today. I'm interested in buffer overflows. So let's see what happens when we break the rules. What happens if I pass in a message that is too long? So that seems okay for now. We were able to go beyond 10. I know it doesn't fit in my array because my array only has 10 characters in it, but things seem okay so far. No behavioral changes, but let's make it longer. So if we keep making the message longer and longer, eventually we're going to see that it starts to break and it starts to give me an error even when I give it the correct password. So that's a little confusing, but things get worse. Because I can do something like this, I can actually stick Jacob here at the end, and then I can use Jacob as the password and things check out. Confused? Let's take a look at what happened. First off, let's look at the program's symbol table and see where our variables are located in memory. Now, I'm using object dump to do this. I did a video about object dump a while ago, link in the description if you missed it. But simply this lets us see the addresses where these variables are in memory, and notice that they are right next to each other. The addresses are in hexadecimal, so they are 16 bytes apart. So when I overwrite the end of buffer, at first it's okay because there's 16 bytes. It has a few bytes of cushion, but eventually I start overwriting the password. And so I can then replace the password with whatever I want and basically change the program's behavior and get it to accept any password that I want. Now, in this case, I changed the password, but buffer overflows allow a wide range of attacks because it really allows me to arbitrarily change any memory that comes after the buffer. So depending on where things are in memory, I could change the code, I could write my own code in there, and then sometimes I can actually get the program to run that code. And all of these different attacks, of course, would be more complicated, and I don't really have time in a short video to go through all of these and how they would work, maybe in the future. But the point is that functions like string copy make this kind of attack possible. And of course, this example is specifically crafted to make it super easy for me to simply compromise in the way that I just showed you. Other programs may be more challenging, and just the presence of a buffer overflow doesn't necessarily mean that you can get compromised, but it's a very dangerous thing to allow, and it can cause all sorts of problems for you. And it is specific to the compiler. If I use a different compiler that happens to put things at different locations in memory, or maybe it allocates my space for my variables differently, well, I may have to actually attack in a very different way, and maybe those things will actually make the attack not work anymore. Because really I'm taking advantage of knowing where things are in memory to do this attack. But so what do you do as a programmer if you want to avoid buffer overflows? First of all, you want to keep an eye out for any time that you are accepting input from a user, especially if you don't fully trust that user to play by the rules. So anytime that you're reading input from the user from the terminal or from standard in or from the network or from a graphical user interface, whenever you're receiving data from a user, you need to be careful because you don't have control over what they send you. So anytime this is the case, you want to make sure that you don't use functions that don't check the length of the input that's coming in. And I've already talked about how string copy is this way, but there's also functions like gets. Gets just reads a line of text from standard in and it doesn't check how long it is. It just keeps going until it reaches a new line character, and so again, there's an opportunity for buffer overflows. And one thing you'll notice is that there are warnings in the documentation for both string copy and for gets that basically warn you about this problem, and you can see that here and here. So let's really quickly look at some safer options. String copy has a safer counterpart, string or strncpy. It's just string copy, but it's got an N stuck in there, which takes an additional number that tells you not to copy more than that many bytes. And if I change my example to use strncpy instead, well then our little attack no longer works, and that's nice. Now, some programmers complain that strncpy is slow, and it is slower than string copy, but the difference doesn't usually matter for most programs. But if it does matter for you, if you really need to squeeze every last bit of speed out of your program, then you can always use string copy, and just make sure you check the length of the string before you copy it. And then of course, if it's too big, don't copy it. And of course, anytime you know where a string comes from and you can guarantee that it will be small enough to fit inside your buffer, well, then you can use string copy without any concerns because you know it will fit. But many people recommend just using strncpy or checking the length because it's easy to make mistakes, it's easy to forget, it's easier to think, oh, this is safe, when in fact it's not because it depends on user input. Also, if you're wondering about gets and safer alternatives, you can always use fgets, and that's, you can see that here. It is safer, it limits the input size. And there are a lot of other places you can get in trouble with buffer overruns. There are other functions that you can run into trouble if you're not careful, like scanf and sprintf. But that's all the time I have for today, so hopefully this is helpful. Hopefully it makes you aware of this issue in your programs. Hopefully now that you're aware of it, you can craft programs that are less vulnerable to this kind of attack. And I hope that's helpful in the future code that you write. So happy secure programming, and I'll see you in the next video.